Thank you, Christina. And I am very honored to be here and give you an overview of our new SSERVI team. It's called CLEVER, Center for Lunar Environment and Volatile Exploration Research. It's a very large team. There's roughly 30 co-investigators, primarily from the United States, but there's another 10 that are joining us primarily from Italy. Simone Parada actually helped us connect to a number of active lunar scientists in the ESA network, and we're going to be working with them. The CLEVER node is actually an integrated systems level approach to characterizing and understanding the lunar environment with a pretty heavy emphasis on the volatile inventories, which we all know is required for near-term human exploration missions. Obviously, this is required for a sustainable presence of humans on the moon. So I'm not a real fan of org charts, but here's one because it does display a lot of useful information, and in particular, the primary individuals that are involved in the leadership of our team. So in particular, Frances Rivera Hernandez, she's the deputy PI. She's a faculty member in the Earth and Atmospheric Sciences Department at Georgia Tech. She's quite active in studies related to Mars. And so she's actually doing sort of the inverse of moon to Mars. She's going from Mars to the moon. And she's moving into lunar science intellectually. Theme 1 is led by Brant Jones. And I'll get to the details of what these themes are, but I want to point out that there's a lot of different institutions that are involved in this. And there's a lot of different disciplines that are involved in this. We're particularly interested in bringing in people from outside the NASA community. And by that, I mean they have tool sets and areas of expertise that are incredibly useful for lunar science, but they may not necessarily have been involved in it prior to their interaction with us. So theme 1 is led by Brant Jones. Bill Farrell's a big part of this. He's from the Space Sciences Institute. Shuai from the University of Hawaii. Toshi, who is actually also on Erasmus. It says Auburn University, but Georgia Tech has recruited him to Georgia Tech, so he's now with us. So I have to change this slide. And then Micah Scheibel, Johannes Abade, Phil First, and Jagong. Those 3 folks are solid state condensed matter physicists. They did not really work in lunar science before they started to interact with us. Julie Brissett, who's at the Florida Space Institute, leads theme 2. There's Peter and Harry Elizabeth, who I met through Geodes, is now a part of our team. He's at Lawrence Berkeley Lab. He's given a talk later on today. Janine Captain, who's the solo PI, as Tony mentioned. She's at the Kennedy Space Center. Tony and Amanda from NASA Ames are involved, so we're directly coupled to Viper through this interaction. Rosario Gerhardt, they're part of theme 2. Theme 3 is run by Johannes Abate, who's over there in the corner, lining up some ultra-fast optics. He's in the physics department of the University of Georgia. Carl Hibbets, who many of you know, he's at Johns Hopkins. Carl Lang, Earth and Atmospheric Sciences, active in geochronology. That'll be the end of the talk, trying to link some of our nanoscale measurements to geochronology. And up at the top is one of the most important individuals is Rain Bozeman. She's the lead for our activities in inclusion, diversity, equity, and access. Okay, so I'm going to give a little bit of an overview of this first because it's really quite important. So Rain has her PhD in social sciences. She's a staff member of SEISMIC, which is the Center for Integrating Science and Mathematics and Computing at Georgia Tech. It's a well-established enterprise at Georgia Tech. She's connected us to some important programs. One is the GIFT program, which is for high school teachers. There's thousands of high school teachers throughout the state that are involved in this. And so we're going to integrate ourselves into that. She has student exchanges with the Chicago State University, which is an HBCU, which is greater than 3,000 students. We are always active in the Atlantic Science Festival, Dragon Con. For people who know about this, we're the host for Dragon Con, Atlanta is. And we're going to set up a science communication blog. Francis is more active in the education side of this. She runs the planetary science seminars. We have a postdoc in early career network called Explorigins. Actually, Micah Scheibel was one of the founders of this, and he's in the audience, which is a postdoc in early career network enterprise. There's a planetary mission design course. And then we're going to, promote much more direct interaction in Lunar GradCon. I actually want to stick, move down to the bottom part of this. We're going to work with CAST to develop Braille books for space weathering and lunar dust. And then I do want to accentuate a long-term and very important relationship we have with Freedom Middle School. It's a middle school in the greater Atlantic area, which is heavily populated by underprivileged and refugee students. And we've had a long-term relationship with them. And this program allows us to sort of amplify this and continue it, which is really important to us. Okay, so now I'm going to move on and explain really briefly what's going on in our different themes. As with the other survey nodes, we have, primarily 3 themes that are all related to understanding sort of the radiation effects from the solar wind. Now, I apologize for this slide. I'm not implying that the moon has the mass strong enough to act as a gravitational lens and bend these photon fields. This is artistic license, but what we do see here is the solar wind comes in, and we got to look at what the electrons and the protons and all the components of the solar wind do in terms of stimulating the formation of volatiles, in particular hydrogen and methane and water. That's the first part. And then theme 2 is trying to understand where they go and what their optical signatures are and how we might find them and use them. And that's coupling directly to Prime 1 and Viper. And then theme 3 is understanding that when we do these impact events, or we have radiation or the solar wind interacting with the regolith, it makes dust, and the dust charges, and we're trying to understand the physics of the dust charging, and then eventually some kind of a geochronology and a way of doing sort of dust mitigation. So these are all connected. They've been drawn as separate themes, but the reality is they're all connected, and there's sort of cross-fertilization between each of these activities. But I would argue most importantly, there's direct interaction with the Prime 1 and the Viper team so that we can do measurements with them that could then be integrated into some of their ops. Okay, so solar wind formation of the volatiles, their production and evolution. This is an important slide to me because my background is more from an atomistic level. And so what we do is we have some first principles atomistic models that then link directly to mesoscale models that then directly are related to macroscale models. So we have this continuum of modeling that overlaps. But then that requires, if we're looking at it from an atomic or molecular level, we need to have tools that give us this atomic and molecular information, but in a spatially resolved manner. So we're bringing in a number of new state-of-the-art nanoscale sample mapping tools, and that's where my solid-state physics friends come in. And this provides the relevant parameters we need to do the accurate modeling. Okay, so I'll go really quickly through some of this. I won't spend very much time on task 1 because I'll be talking about that specifically this afternoon. But the point here is that when we look at the solar wind, we have to look at the ions and electrons synergistically of what they do, and they're very much involved in forming the volatiles that we're caring about. The other one is, so that's the atomistic side of it, but we look at sort of the impactors themselves, and we are looking at a lot of impact events, but they're much smaller scale than the ones that Bill was talking about, where they're making craters. We're looking at much smaller impact events. We're using similar modeling, the ISALI approach, but we're looking at how these impactors redistribute the volatiles within the craters. And they sort of mix the crater up. And so it's more focused on what it does for volatiles and moving volatiles. On the left here is sort of a mapping of the hydrogen or proton mobility through different zones here. And then there's how you use this information to do some overall mapping from an impact event. I'm going to speed it up here. Space weathering effects on the volatile content and distribution. We want to characterize the permanently shadowed regions of mixed ices, making simulants very similar to what Dana was saying. But we want to pay attention to something. They're permanently shadowed, but they're permanently shadowed from photons. They're not permanently shadowed from radiation interactions. And so when you look at this, you realize that the ice is never going to be clean, and they may have a lot of toxic molecules within the ice, which we need to sort of understand. And we'll like to work on getting ground truth measurements for modeling the capabilities for the traverse planning and execution during volatile mapping. So we have, these systems where we make these simulants that are covered with ice or submodel layers of water. We interrogate them. We actually have a sample holder that can be cryogenically pulled back and used to transfer these cold regolith samples over to another chamber. We could do optical microscopy. That's on task 2. This is the infrared reflection measurements using the spectrometer in our lab, but we'll be doing something very similar using the spectrometer on Viper. Christina Buffo is going to give a talk on this afternoon. There's another talk this afternoon on volatile diffusion and transport. This is very important to us because we can measure actual diffusion constants in these cold regolith samples, and we can get topographic or tomographic three-dimensional information on these materials using techniques that Harry's going to talk about. That brings us to the third theme, which is looking at the physics of grain charging, grain-grain interactions, and then ultimately, how these, processing of the grains might be related to geochronology or radiometric dating, and then some approaches for dust mitigation. Okay, so the theme focuses on fundamental radiation effects and related to geochronology, and then ultimately dust mitigation. So again, there's an example of using these electrostatic force microscopy tools where you can look at the amplitude and phase and look at differential charge zones within a grain. So you can map out the charge differentials on a grain and see what happens on a grain to grain basis. And then we can look at multiple grains as well. This is useful for us to understand how we might want to develop some strategies to mitigate charge or dust effects on spacesuits and whatnot. The last one is how these charging states that lead to charging might be related to geochronology. You have to understand what the nature of these defects are and whether or not they're electron trap states or they're sort of fission tracks, things that are made by fission tracks, and sort of back calculate to, how they were made and what the radiation inventory might be. And this is useful for getting some information on geochronology. So with that, I'm going to just leave you with this slide that absolutely nobody can read, and I can barely read it myself. But it does illustrate that we are already connected to a number of teams. There's a lot of people involved in this. And most of the good work comes because we're working with a lot of other survey teams, and we're going to begin interacting with some of the other new survey teams. And that, to me, is one of the beautiful parts of being part of this very open community. So thank you for allowing us to be here.